started. So it's a pleasure to have with us Shuran Song. So Shuran is a professor at Columbia University. Before that, she was at Princeton. Like many people who are doing robot learning now, she was working on 3D vision first, right? And I remember her giving her oral talks, in CVPR and all the vision conferences. Then I think she moved on and she participated in the Amazon Robotics Challenge, working on affordance-based reasoning. And more lately, I think she has gone full on into robotics with a lot of cool stuff on dynamic manipulation, which we are very excited to hear. Now, in the process, Shuran's work has received multiple Best Paper Awards and Best System Papers Award. And also Shuran herself has received awards from the Sloan Foundation, Toyota, Amazon, and the list goes on and on. So Shuran, it's a pleasure to have you. As you said, I wish, this could be in person, but, hopefully in the coming years, we'll have an opportunity to have you over in person. Now, before I hand it over to Shuran, let's also thank Tao Chen for helping organize this seminar. So thank you, Tao. And Shuran, super excited to hear your perspectives and your, exciting work. Please take it away.
Thank you. Thank you so much for the introduction, and super happy to be here. And hopefully we can see each other, like a lot of people in the upcoming conferences, like ECRA and or RSS. RSS will be in New York in Columbia. So hopefully we can see each other. Cool. Yeah, so let's start on my today's talk. So actually on my first slide, I put 3 links to all the projects I'm going to talk about, and actually those web pages include all the links to all the videos, just in case there are any issues with Zoom's sharing or network bandwidth that you cannot see those videos in full speed, then you can still go on those to those websites to check out those videos. Okay, so today my talk is about dynamic manipulation for deformable objects. So it is a talk about deformable objects. So I often like to start by just simply remind us how common deformable object is in our everyday lives. So here is just trying to depict a typical morning routine for most of us. And as you can imagine, within the first hour of our day, we already interact with a large variety of deformable objects. And we can easily and robustly manipulate most of them without really think too much about it. However, this kind of seemingly trivial task of accurately manipulating deformable objects is still a very big open challenge for today's robotic system, which are often designed to handle rigid objects with very rigid movements. So, however, different from the rigid objects that we always think about and design algorithms on, deformable object often has a much complex dynamics due to their extremely high degree of freedoms. Many people even say that it's near infinite degree of freedoms. And what makes things even worse is that among all these degree of freedoms, there's only a small number of them can be directly controlled by the robot through the contact. So in other words, this kind of system is often highly under-actuated once you kind of involve deformable objects, especially for objects like cloth, right? So for example, if the robot is kind of holding a piece of cloth like in this image, all it can control is a very small region on the cloth around its gripper, right? And the rest of the cloth is just hanging there, and the robot does not have direct control over those out of contact positions. So as a result, those typical actions that we are manually designed for manipulating rigid objects, like pick and place actions, are often highly efficient for deformable objects. Since each time, each interaction step, only a small area or small region on the cloth can be affected by this kind of actions. And also, in addition to just efficiency, this kind of a pick and place action also limits the range of tasks a system can really perform. So for example, if the robot is trying to unfold a blanket that is larger than its kinematic reach range, it will never be able to fully unfold its cloth through a pick and place actions. So I think this choice of using quasi-static actions has really become a common limitation for many power works in cloth manipulation. So although there has been many works that try to study quite sophisticated algorithms and models to kind of model deformable objects, the resulting system oftentimes still inefficient, where they can easily take hundreds of steps just to manipulate a small piece of cloud. However, on the other hand, we humans manipulate deformable objects in a very different manner, where we often use very fast and fluid action that fully leverage the dynamics of deformable objects in order to quickly achieve our goal. And I think formally, we can try to categorize these two types of manipulation strategy as dynamic and quasi-static manipulations. So the difference between these two categories is that in quasi-static manipulation, the system always tries best to avoid task dynamics by using slow and careful movements. So most of the time it assumes that the environment or the object or the whole system is static as soon as the robot stops moving, right? On the other hand, dynamic manipulation will try to, instead of avoiding dynamics, is trying to embrace and leverage those dynamics in order to manipulate an object. So fundamentally, what dynamic manipulation allows the system to do is to make use of the accelerations in the action in order to control those out of contact positions on the objects, and therefore obtain more control over the total number of degree freedoms of the object. And this capability of dynamic manipulation, I think, is directly addressing one of the core challenges for deformable object manipulation that is caused by their high degree freedom and under iteration. So here are just a few examples of possible dynamic actions or strategies that can be used to manipulate deformable objects, such as fling a cloth, or swing a rope, or opening a deformable bag with active airflow. So in these examples, we also try to highlight the locations on the objects that is being manipulated by the system, however, are not directly in contact with the robot throughout the manipulation process. Yeah, so today, in today's talk, we are going to get into details for some of those examples. But before I do that, I want to put out a question. So if dynamic manipulation are so well suited for deformable objects, then why we are not yet using it for manipulating deformable objects? Right. So what are the main barriers that's preventing us using it? So I think I could summarize three major challenges. So first is the action sequence complexity. Right. So for example, if we designed a simple pick and place action, we can easily parameterize them with only two locations, the pick location or the placing location. However, specifying a dynamic action, it often requires to also, in addition to specify the positions, we also need to specify the velocity and acceleration. Therefore, the learning algorithm for dynamic action also need to kind of be able to handle this kind of much larger or expanded actions parameter space. And the second challenge, I would say, is the complex object dynamics, which is quite obvious. So an object under dynamic action is highly influenced by its physical properties, right? So many of them actually are very hard to measure, especially for deformable objects, such as their nonlinear stiffness, or like all those things is actually really hard to measure and therefore model. And therefore, it really requires the policy or the system be able to actively adapt to it. So that's the second challenge. And I think the last challenge I also want to highlight is this big sim to real gap. So I think at this moment, cloud simulators is still very far from perfect, although we already observed like a really good and big progress, but they're still not perfect, especially when dynamics are involved. So what this means is that we kind of really need a system that can either effectively collect its own training data in real world, or be able to robustly perform sim to real adaptation in order to bridge this gap. So those are the three challenges I think that we really need to address in order to achieve a dynamic manipulation for deformable objects. So in today's talk, I will try to show some possible solutions for all these challenges with three of our recent works. So we'll start with relatively simple tasks like cloth unfolding that may not require very precise control and planning. And then we'll move towards a more challenging task that actually is goal conditioned and also as a result has a much higher requirements on the precision. So first, let's talk about FlingBot. So this is actually our first attempt of using dynamic manipulation for the task of cloth unfolding. So, is there a question? Then I will just move on. Okay, so class unfolding. It's actually a very simple task if you just want to describe the objective. The goal is just to maximize the visible area of a class. So this task is also can be considered as a common first step for almost any class manipulation pipelines. So for example, if you just want to know whether this crumpled class is a t-shirt or a dress, the first step is very likely you're going to unfold it in order to see the full surface areas of the class. However, just like many tasks in robotics, while the objective is simple and easy to describe, doing this task robustly and reliably is still very hard for robots. So here I'm just showing you a video of two-arm robots trained to unfold a t-shirt using this kind of traditional pick-and-place actions. So you can see that it actually takes the whole system very long time to make very small progress. And if the class or the t-shirt is actually larger than the robot's reach range, the class will actually never be fully unfolded because of that limitation. So what that means is that in your real life, if the blanket is longer than your arm length, then you are never able to fully unfold the blanket, which is not very ideal. But obviously, that's not how we would unfold a blanket. So instead, we will probably do something very similar to this video. We will grasp the class with two arms and then fling the class with high velocity in order to unfold it. So what this example showed us is that what the robot really missing is the capability of using high velocity dynamic manipulations, which is also the key idea behind FlingBot. So using this idea, we're incorporating high velocity fling action. FlingBot is able to achieve over 80% coverage within 3 interaction steps. And the system also able to work on cloth that is larger than its physical reach range and also generalized to different shapes of garments while it's only trained on rectangular cloth. So in the following slides, we're gonna provide a little bit more details of how we can do it. So here is the physical setup that we use in real world. We use 2 UR5 arm and also 2 RGBD camera. One is taking a front view picture of the workspace. So basically, it will take a picture of the class being picked up, and that is actually used to perform this stretching action that's going to talk later. And then the second camera is actually our main camera that is taking top-down image for the whole workspace. So that camera is actually used to both generating the input for the policy and also computing the reward using the coverage area. And then what the algorithm do is trying to take the top-down image as input and then output the parameters for the Fling primitive, which we're going to talk about in a bit. And then after each action or after each of the interaction, the top-down camera will capture an image of the class and compute the delta coverage before and after the interaction. And then the whole system will use that delta coverage as a supervision signal to supervise the network training. And in the end of each episode, the system will automatically reset the class initial state by randomly picking up and then drop back to the workspace. So the whole system is able to just learn through self-supervision with minimal human intervention. So from time to time, we need to switch out the clock, but between that, we can just let the system to automatically collect training data to self-supervisedly learn how to fling the clock. Okay, so here is a little bit more details about our Fling primitives. So we actually designed the primitive with 4 steps or 4 stages. So first is pick up the class and stretch it, and then fling the class with high speed or high velocity, and then finally place it back to the workspace. So to perform this primitive, what we need to, the network or the system need to do is to decide where to pick, how far to stretch, and how fast to fling, and then finally where to place the class. Right. So however, for all these 4 different steps, some of those steps is actually has pretty straightforward answer if you consider the task of class unfolding. So for example, we because we want to unfold the class, so we always want the class to be stretched as much as possible. And for the placing, we can just let the system to place down the class in the workspace as long as it's easy to pick up again. Right? So that is something that the system actually do not need to explicitly learn. So at this step, then what we left is learning where to grasp and how to fling. And in our actually one observation we have in our real world setup is that we kind of find that the grasping location is actually much more important compared to the flinging speed or the fling parameters. So for example, if we vary the fling height and or fling speed manually, the system can still able to achieve a very good unfolding performance as long as the grasp position on the t-shirt is good. So for example, if the grasping location is on the shoulder of the t-shirt, then there's actually a very wide range of fling speed or fling height that can fully unfold the class. So the system is actually not that sensitive to those parameters. So in order to simplify our system, we actually fix the fling speed and instead focus on only choose where to grasp the two grasping points. So what we just did is try to reduce this very complex task of learning parameters for this complex multi-step primitives to a much easier task of learning where to, how to, like, what's the good grasping locations on the car. However, just to learn an effective grasping strategy is still a tricky task, especially if we consider two robot arms. In order to avoid collisions, we actually need to make sure that those grasp predictions satisfy certain constraints. So those constraints is actually quite obvious. So for example, they need to satisfy a crossover constraint, means that the left arm only pick up the left side and the right arm, the grasp prediction is on the right. The second constraint is called grasp width constraint, which means that the two grasp points cannot be too far apart or too close. And then given these two constraints, what we need to do is to design our action parameterization that can easily satisfy those constraints. So a straightforward formulation is just directly predicting the left and right grasping points independently. However, those kind of constraints will actually just get entangled together, and therefore it's actually quite messy or like kind of hard to filter them out afterwards. So instead, what we do is that we change the action parameterization into another formulation. So which we predict the center position of the left and right grasping point, which we labeled as C. And then additionally, we predict the angle of this line between these two grasping positions, which we've called theta. And then we predict another parameter, which is the grasp width between these two grasping points. So this parameterization allows us to directly compute the left and right grasping position with very simple trigonometry, and the resulting grasping position always satisfies the constraints that we described earlier. So now what we need is just a method to learn those parameters. So again, one approach is we can directly predict those four parameters like C, theta, and W. However, we can significantly improve the learning efficiency by injecting some kind of inductive bias to the learning process. So in particular, we observed that the task of class unfolding, actually the best grasp position has a few equivariants that we can leverage. So this kind of equivariance is in particular between the input image and the output grasp parameters. Right? So for example, the best grasp position should be translational equivariant, which means that if the class is shifting around the workspace, the grasp point should be shifted together. And similarly, it should also be equivariant to rotation and scale. So to implement this idea, we enforce this equivariance, we use a spatial action map as a value network to evaluate all the grasp candidates. So the key idea for spatial action map is that whenever we need to reason about rotation or scales in the output, we can offload this reasoning to transforming the input image. So in other words, instead of rotating and scaling our grasp parameter, we can rotate and scale the image and then infer the score for fixed grasp parameters. So for example, given an input image, we can scale and rotate to obtain a collection of transformed image. And then where the scale will corresponding to different grasp widths and the rotation corresponding to different grasp angles. And the output is a dense value map where each pixel corresponding to one possible center location of the two arms, which is the parameter C that we talked about earlier. And then the action selection is done by simply pick the pixel with the highest grasp value among all the scales and rotations. And then the value network is trained to predict the delta surface area with self-supervised learning. So here I'm going to just jump into some real-world experiment results, and we're going to show you some comparisons to pick-and-place systems. So here we actually, on the left is what we compared is the pick and place system, and on the right is our FlingBot system. So below you can see the plot, which is the class coverage with respect to interaction steps, which shows the efficiency of different policies. So here is a result for a larger rectangular class. As you can see that FlingBot is able to fully unfold this class within 4 interaction steps, and however, the pick and place system will take much longer time to make smaller progress. And here is another example for t-shirt. So actually the whole system, as I described earlier, is only trained on rectangular cloth. So they actually never see t-shirts in the training, but it's able to work reasonably well for different shapes. So here are a little bit of quantitative result and comparisons. So we compared with 2 quasi-static baselines, which is pick and place and pick and drag. And we here also can include a variance of our approach that actually indeed learn the fling speed on top of the grasping strategies using reinforced learning. However, what we observed is that it is not so much better than the original FlingBot. So we actually decided to choose the simpler version as our final approach. So to summarize FlingBot, I think probably the most surprising thing we learned through developing FlingBot is that even without explicitly model the class state or using any complex learning strategy, FlingBot is able to work pretty well for the task of class unfolding. And I think this kind of simplicity of our approach really underscores the key takeaway for FlingBot, which is dynamic action, just really good for class unfoldings. And to address the challenges associated with learning, we introduced action parameterization, which provides collision and learns the value network that make use of the equivariance of the problem structure in order to improve learning efficiency. So before I move on, is there any questions about this project?
Shuran, maybe one question about the type of cloth. So does it matter if it is cotton or wool or silk, or does the same flinging strategy work fine for all of them till the time you fling it hard enough?
Yeah. So actually, that's a very good question. I think it's the short answer is it definitely depends on the material of the class. And one, as we'll show later, very soon, is that once your class getting really heavy, then it's actually will cause trouble, and the FlingBot will not be able to work. So in general, lighter class works better just because of the limited speed of the system can produce.
Thank you.
Mm-hmm. Okay, then we can move on. So yeah, so indeed, I don't want to give you the wrong impression that FlingBot can solve all the class unfolding tasks, right? So actually, there is a few limitations I want to go over. So for example, one typical failure case is when the class getting heavier as when they have different materials or just simply larger, right? Well, in those cases, the robots will not be able to produce sufficient speed in order to fully unfold the class. So here is actually an example of a long dress that we put in the workspace. And actually, no matter how many times FlingBot try, at most it can only half unfold the class because it's much longer. And in those cases, actually just simply increase the robot's action speed. Oftentimes it's not a valid option because either the hardware has limitation or sometimes it will become too dangerous for the robot to execute those high velocity speed, high velocity actions, especially if the robot needs to work around human, then it's considered as not very safe. So in our follow-up work, in order to address this problem, we introduced additional error dynamics in order to manipulate class. So we call this system DextAlRity with error in it. So in this work, we let the robot to control the additional error blower that learns a closed loop policy to kind of control the direction, the blowing direction. And then in this case, the system can easily unfold a diverse set of class, including this large dress. And note that in this new framework, we could easily replace all these 3 arms with a much cheaper and a slower robots. We don't necessarily need to use the R5 because we no longer need to introduce those high velocity actions by itself. The RPOM is also actually very cheap, and you can easily purchase it from Amazon with $20. Right? So the whole system has the potential of become much easier to deploy. And of course, in addition to unfold class, this idea of using error to manipulate objects can actually also be applied for many other applications, right? Such as opening a deformable bag by blowing errors into the bags, or blowing leaves, or other small particles into a target area. So in general, I think this kind of error-based manipulation really allows the system to kind of simultaneously apply forces in a dense 3D space without direct contact, which I think is a pretty unique advantage compared to the traditional type of contact-based manipulation. So I think it is a very interesting direction to explore more, like how we can better use different modalities like error to manipulate objects. So today I will not get into details about this collection of work, but feel free to check them out on the website. And apart from handling large fabrics or cloths, another limitation for FlingBot is its limited capability in handling goal condition tasks, and especially if your task has some precision requirements. So in the class unfolding task, it's actually indeed a very simple task because the algorithm only need to care about the total coverage of the class without really worry about the actual configuration of the garment in the end. So in the end, as a result, all the configurations that I'm showing here, they could be considered as equally good. They're like fully unfolded for this task of unfolding, but they are obviously not sufficient for many real-world applications where you actually really want the particular class get into particular configurations. So which is much harder requirements, and also we can just in general call this requirements of goal condition manipulation. So in the next project, we'll actually focus on another category of manipulation task, which is goal conditional manipulation. And we're going to talk about how we can design dynamic manipulation system that's to handle those tasks. So what is a goal conditioned task for, especially in the context of deformable object manipulation? Right, so here are actually two examples of those tasks. One is trying to swing a rope to hit a target position. The other is to swing, for example, take table class or any type of class into a target configuration. So in both tasks, the goal condition, the conditions are defined by the target key point positions. So the key points is either, in these two cases, either on the tip of the rope or the corners of the class. Right. So once you define the key point locations, you basically define the goal conditions. And then the goal for this algorithm, the policy, is to generate actions to achieve those goals. And since in both tasks, the target are still outside the system's reach range, therefore it still requires the system to use dynamic actions. Pick and place will not be able to reach those goals. Okay, so actually there is a good reason. That's why we try to avoid this task in our earlier works, like for example, FlingBot, that we actually on purposely avoid to do this kind of goal condition task. And the reason is simply because they're too hard, right? And we have been trying to look away from it. And here is concretely the reason why we think they're too hard. So first, unlike quasi-static manipulation, objects that a motion under dynamic action is actually influenced by many of these physical properties. And also at the same time, for deformable objects, many of those physical properties are actually very hard to measure and even estimate, such as their nonlinear stiffness or density distributions. So as a result, this combo of dynamic and deformable makes it extremely hard or difficult for a robot to plan its action to achieve a precise goal conditions. And in fact, I would argue that it is a task that's even challenging for human, right? So given a new rope, I think it is actually very unlikely for us to hit the goal location with the first few trials. However, the good thing is that after a few attempts, we are often able to get closer and closer to the goal and eventually reach the goal conditions. So what do we learn through this kind of trial and error process, right? So how we can improve our action? Do we actually try to, through this few trial and errors, do we try to learn a model that maps our action to the full trajectory? I think probably not. At least I cannot do that. And or do we actually try to decode the physical properties about the rope such as their linear densities? I guess probably not either. So instead, I think what we are really rely on is actually a good intuition or prior knowledge about how to adjust our action in order to affect the resulting trajectory. So for example, we know that swing harder will in general make the rope go higher, right? And if we extend our arm more, it will let the rope reach further locations. And then we can rely on this kind of intuition in order to adjust our action in order to get closer and closer to the goal. So in this work, we call this intuition residual policy, where our hypothesis is that the knowledge about this kind of change or how the action change will change the trajectory is much easier to learn, and also in most of cases more transferable to different ropes. So based on this intuitional observation, we propose an algorithm called Iterative Residual Policy, where at its core, the algorithm learns a delta dynamics model that takes in an observed trajectory and a delta action as input, and then try to predict an updated trajectory after applying that delta action. So here, the robot's action is parameterized with its target joint angle and the maximum joint speed. And then by sampling different delta actions and then predicting their corresponding resulting trajectory, the algorithm could iteratively select a better action that will get closer to the goal. So that is the general idea for the system. And then in this case, the selected best delta action will be applied on top of the current action for the next iteration. And then as a result, the system can iteratively improve its action and then finally, hopefully achieve the goal. So a note here is that for this delta dynamics model, it's actually entirely trained in simulation. And as you can imagine, for this task, there is a huge sim to real gap between the simulated rope and the real world experiment. So here is actually like two ropes that we actually manually measure their physical parameters, their length and density between simulation and real world. And you can see that the resulting trajectory is actually very different between simulation and the real world. However, our hope is that the learned delta dynamics, especially its just general direction, can be generalizable to real world and objects with different physical properties. So as long as, even if the actual prediction accuracy is not that high, but as long as the direction is correct, then it can help us to lead to the actual solution. So here is the system in action. So at each iteration, the rope trajectory is actually tracked by a calibrated camera. And then the distance to the goal is measured by the shortest distance along the trajectory. And then the algorithm will, at each iteration, the algorithm will sample a set of delta actions and predict their trajectories using the learned delta dynamics model. And the action associated with the smallest distance will be selected for the next iteration. So in this visualization, the best trajectory will always show it on the top. And the process will repeat until it's reached to the goal or reach the maximum iterations. Cool. So yeah, so that's the system in action. And in our experiments, we actually try to systematically validate or test how well the system can generalize, especially whether it can generalize to, for example, real-world dynamics when it's only trained on simulation, whether it can adapt to objects with unknown or new physical parameters, and also whether the system can adapt to different robot hardware embodiments. And in all the following experiments, I'm going to focus on showing you the real-world results while the model is trained. It's actually the same model trained in simulation. So in the first set of experiments, we want to show the testing results that we just directly deploy that system on different ropes. And many of those ropes actually are significant auto distribution. For example, the bow whip actually has a nonlinear density, while in simulation, all the ropes is actually uniformly, the density is actually uniform throughout the rope. And similarly for this, there's also a long cloth. It has much higher air resistance. Once you can see it swing, it's actually also very different from the training rope that we use in simulation. And then before I show the results, I want to just again highlight how challenging the task is. So here we actually show the rope trajectory captured under the same robot action. So the robot's action is the same. However, due to the different physical properties on the rope, such as air resistance or mass distribution, the resulting trajectory can vary drastically. Therefore, the robot really needs to adapt its action or policy based on visual feedback in order to generalize to novel ropes with unknown parameters. So here is actually the resulting trajectory after the system converges. Again, the model, we test with a single model trained on simulated data. And you can see that the algorithm will be able to choose using different actions in order to achieve the same goal. And the action is actually choose to accommodate different rope dynamics. And next, we also further validate the system's generalization capability with respect to different robot hardware or hardware embodiments. So what we do here is that we basically change the length of robot's last link, which basically change the mapping between robot's action and its effects, right? Because the last link has different lengths now, the same joint angle or joint speed will actually result in very different effects or actions on the rope itself. So in this case, the system is kind of forced to adapt to all this new kind of embodiment using its visual observations of the rope trajectories. So in our training, we actually use the 50 centimeter length as our training embodiment, and both the longer and shorter links is out of distribution. So here is the result. As expected, for the rope that has a similar length, or like for the setup that has similar length compared to the training setup, it actually had start with much lower initial error. But for all different three different systems, they all able to quickly adapt according to their visual feedback and reach to a good performance in the end. And then in the next experiment, we try to just stress test the system and then see how robust it is or how quick it can adapt to unexpected changes in the system. So what we do here is we first just let the system converge on a given rope and a given go conditions. And then we try to interrupt the system by tying a few knots on the rope. So effectively, by tying a few knots on the rope, what we changed is a few pretty critical parameters on the rope, right? So for example, the rope now is much shorter, and also it has a nonlinear densities throughout the rope. So as expected, after that, immediately we can observe a much higher error because of the change of the rope. However, after 1 or 2 iterations, the policy can quickly adapt to the new system dynamics and regain a good policy. So here is the quantitative comparisons. The method on the left is actually a very strong baseline, where the algorithm used the optimal action in simulation optimized for each individual rope. And so for each of the individual rope, we actually manually measured and modeled them in simulation. So that actually can be considered as the best performance you can get if you rely on a physics simulator for the rope. However, it still results in more than 20 centimeter error, which really highlights this very big sim-to-real gap for this task. And we also compared with method used, for example, system identification and the linear dynamics model. And we found you can actually find more details about the comparison in the paper. But so the takeaway is that our method works better than those method baselines. And apart from swing a rope, we also want to kind of demonstrate the generalities of our method, or this methods of iterative residual policy. So what we try to do is we try to apply the same method or the same framework to a cross placement task with minimal modifications. So the goal for this task is trying to swing and place a cross on a given target position where the pose is defined by 9 different key points located on the cloth. Right? Again, the algorithm does not know the physical parameters of the class, therefore it needs to adjust its action accordingly based on the observed trajectories. And the one modification we need to make is that different from swinging a rope where there's only one key point on the tip of the rope. In this case, we actually have 9 different key points. So the input to the policy is actually a stack of image of 9 key points corresponding to each of them. And then the output of the system is also 9 different key point trajectories. And however, the policy, the idea and the framework is the same. It will iteratively sample different delta action, predict its trajectory, and then select which one will get closer to the goal. Okay, so here actually I'm going to show you 2 typical strategies that's actually acquired or learned by the policy. So first, in the first example, in the first step, actually, regardless of the class, they actually start with the same action, initial action or initial fling action. And then in the first example, the class is a bit too close to compare to the goal conditions, whereas the goal is actually further away from the placing location. And then in the second example, actually the class folded by itself due to the high densities on the class. So it actually bounced back to fold by itself. So in both cases, actually, the system needs to adjust their action accordingly and differently, right? With that, the first observation of the trajectory observation, the policy actually decided to increase its stroke in the first case in order to swing further. But in the second case, it actually decided to decrease its speed in order to prevent the class folding by itself. And after that, the system will basically continue to adjust its action until it achieves its goal. So this task typically takes 3 steps to converge or reach to a good conditions. So as you can see, this formulation of iterative residual policy is actually pretty general, as it can actually be applicable to many repeatable tasks with complex dynamics. So here I want to highlight it's repeatable means that the system actually cannot rely on its automatic reset mechanism, because if you cannot, after you swing the rope, you cannot reset the rope back to the original position, then actually predicting residual, like the delta dynamics cannot really be applied for the tasks. Means that your initial state will be different, therefore the whole system needs to adapt to different initial state as well. So there, that is the biggest assumption for the system, is that the whole system needs to be repeatable. And but however, it's able to handle this very complex rope or deformable dynamics because the policy is that the delta dynamics is learned instead of analytical model or rely on a simulator. And then what we learned from this project, I think the most important thing is that instead of learning the full dynamic model that's directly mapped from actions with effects or trajectories, the algorithm can learn and make use of a delta dynamics, which is much easier to learn and also generalizable to many different conditions. So in particularly in our experiments, we test its generalization ability to noisy real-world dynamics, different objects with different unknown physical properties, and even different robot hardware embodiments. So that is for the product of iterative residual policy. And then now I'm going to kind of try to summarize. I think if you want to just have one sentence takeaway from today's talk, I hope that you can remember the importance and the benefits of incorporating dynamic actions in deformable object manipulation. Right, so I think the reason is that by leveraging the dynamics or in general accelerations in action, the system will now have a much better opportunity to address the core challenge in deformable object manipulation, which is caused by its high degree of freedom and under iteration. And then if you care how to make it work, or like the details about how you can make dynamic manipulation work for deformable objects. So here are some practical lessons that we learned through our projects. So first is that in order to handle this kind of complex action sequence, we often design and use different action primitives that maps a very high action sequence into a low dimensional parameterization, right? Which is much easier to learn and it reduces the complexity for learning. So for example, we can simplify the problem of learning the complex fling action into just predicting where to grasp. And then in the last project, we parameterize the whole swing action of a rope as its target, joint, angle, and speed. And then in order to handle complex object dynamics, we could always benefit from some feedback controls that and simplify the learning problem using delta dynamics, which is the example showed in the last project. And we show that it's much easier to learn and also generalizable, especially compared to learning the full dynamic model that's rely on accurate system identification. And finally, in order to handle a big sim to real gap, I think there are two possible solutions. Ideally, you can use both of them. One is kind of try to leverage self-supervised learning in real world, that you can automatically collect data in real world and automatically label the data in real world. And then another approach is rely on online adaptation, such as iterative residual policy. That's basically just learning how to adapt for different physical parameters. So yeah, so that's the end of my talk, and I'm happy to take questions. For most of the projects, actually, both the code for a real world and simulation system is on our GitHub. So if you want to try out some of the action primitives on your robots, you can take a look. And also, if you are interested in the simulations, you can also take those codes from there. And happy to take questions.
Thanks a lot, Shuran, for the wonderful talk and all the dynamic videos and tasks that your robots were able to do. So, first let's thank Shuran. So any questions from the audience? So while people are formulating their questions, so Shuran, I was curious. I think you mentioned, how do you track the rope position? Is it just a single RGB camera or something else that you're using?
Yeah, so actually that is part of the challenge we need to handle. But so in the end, our solution is actually a single RGB camera. We calibrate it, and then we actually annotate the key points, and we train a key point tracking algorithm to track the key points in real world. It won't work if the object is more complex, if it has several cushions like claws. That's why the claws example we only show in simulation. We are not able to show it in real world. But yeah, so that's our in the end the solution. We actually tried to use two like stereo camera or depth camera in order to try to track the 3D location, but accuracy is not good enough. Yeah.
I see. And then maybe taking, so you talked about FlingBot before, which would, spread the cloth, but maybe not in a goal configuration. Then you ended the talk with folding the cloth in some goal configuration. That presumably it seems like, you would want to fold clothes also at some point, but, that seems, even harder in many ways. So I'm curious, what you think are, some of the hard challenges to go to cloth folding, given where you are at the moment.
Yeah, this is something that we are actively working on, as you can probably imagine. Okay, so challenges. I think first is actually how to define goal conditions if it's in folded state. And so I think it's easier if we think about it's the instance level. If you only has one class, and you can say that you can define a goal for that one class. But what if you want the goal condition to generalize different t-shirt or different shirts, right? So once you want to have this kind of generalizable goal condition, then how to define the goal, I think is the first challenge. And the second is how to have a perception algorithm that works. I think the key point example I gave in the RRP is a way that we try to simplify the perception problem. We only care about one point or like a few points, but if there's occlusions, especially if you want to fold the class, then there's guaranteed to have occlusions. Then how to actually estimate the state of the class under occlusion is very challenging. And once you have that perception algorithm, then how to compute the reward from that perception algorithm with your goal condition, that's another challenge. Yeah, so I think that's probably like the two things in my mind that we're having trouble handling, and I think is the biggest challenge for like if we want to build folding robots.
Yeah, I guess the cloth has the same color, right? So it becomes hard to detect key points or some corresponding features.
Yeah, and I think self-occlusion is really the biggest problem. For a lot of times, if it's not unfold, I don't even know what it is. If it's just black color.
Yeah. So I'll take a pause and see if there are any questions from the audience. No, seems like Shuran, you convinced everyone that this is the way to do dynamic manipulation.
Cool. Yeah, then nice to meet you, guys. And if you have any questions, feel free to email me or email my students. Yeah.
Well, thanks a lot for coming down, Shuran. So I also thank